So, as we said that casein contains alpha, beta, gamma and kappa casein, and the reasons for the hydrophobicity we have discussed, right. We also said that we may be coming across, though we have completed earlier, what is micelle, protein micelle, all these we have said, but casein micelle we will have a little discussion on that also. So, in today's our this course, that is dairy and food process and products technology, in 30th lecture, we will start with casein micelle, right. So, casein micelle is what? Is that the molecules of casein plus minerals, that is calcium phosphate, right. So, casein micelle is molecules of casein plus mineral, that is calcium phosphate, together is forming the micelle, right. You remember in micelle we had given this kind of a pictorial view, right, where we had showed that. So, these are having some thread like linking, where we have one hydrophobic and one hydrophilic, and one hydrophilic end, right. So, those we had said earlier. Now, it is casein micelle is that where molecular casein or molecules of casein plus minerals in the form of calcium phosphate, they associate or agglomerate or they form this bonding, and that is the micelle, out of which the composition is 93% casein is to 4 phosphoproteins, right. So, 93% casein in 4 phosphoproteins, right, in which alpha S1 casein is around 36%, that is alpha S2 form is around 10%, beta casein is around 34% and kappa casein is around 12%, which we had said earlier also. Now, 7% colloidal mineral complex, 7% colloidal mineral complex around. So, 93% was casein, where 4 phosphoproteins were there, and 7% colloidal mineral complex is there, where phosphate, calcium, magnesium and citrates are present. So, the casein micelle, as we said, is comprised of the casein molecules plus the phosphates. Now, these phosphates are around 7%, or the minerals are around 7%, maybe in the form of calcium or phosphate or many others, and 93% is out of the casein, and out of which we have given the distribution of alpha, beta, kappa and alpha S1, alpha S2, right. So, these distribution we have said, and the minerals are calcium phosphates, okay, phosphate, calcium, magnesium, citrate, they act like the minerals and they all put together forms the casein micelle, right. Then, if we look at what this is one of the simplest model of the casein micelle. There are n number of rather this kind of casein Micelle models are there. In earlier class I had shown one. Here also I am showing you another. There are sub-micelles, subunits. Here is chains, calcium phosphates, these are there. So, here is layers are that. This is called the structure with subunits, where the subunits are there, and this is called the open structure, where things are here like this. This appears to be like here, right. So, this is the one model which is there. There are, I said, n number of similar models are there, and as from it is appearing, it is very complex, right. This given some reference also, so that we can cross refer if required, right. Now, this Casein Micelle which we have just seen is what? That is, the polymers are built up of polymers are built up of hundreds and thousands of individual casein molecules and form a colloidal solution. We know that casein is present in the colloidal form. So, this colloidal form, where hundreds and thousands of casein molecules, individual casein molecules, they form these colloids or colloidal state in the milk, right. These molecular complexes are known as Casein Micelle, and this micelle may be as large as 0.4 micrometer, right, as large as 0.4 micrometer, and can only be seen under microscope, because that is why it is called micrometer, that is, you cannot see in naked eye, it has to be seen under microscope. 0.4 is very small, right. You remember the other day we said that dancing of fat globules can be seen under microscope, high resolution microscope, and there the globular size is around 2, 4, 10 these kind of microns, but it is 1/10 of that. So, 10 times magnification if you have, even then you can see 10 times magnification of the microscope which you saw with for the fat globule. So, 10 times of that magnification if you have in your microscope, you can see the protein micelle also. So, it is as large as around 0.4 micrometer, right. A medium size micelle consists of about 400 to 500 sub-micelles which are bound together. These, from the pictorial view, we have shown that these sub-micelles, they agglomerate, they form the chains, and these chains are there around how many? 400 to 500 sub-units, sub-micelles are there, right. So, alpha beta caseins are mainly concentrated in the middle of the sub-micelle, while kappa casein predominates in the surface. So, can you give an why it is so? Because when we discussed about alpha, beta, gamma, kappa caseins, that time we have shown, we have seen rather, or we have told that alpha beta are more hydrophobic, or hydrophobicity is there in alpha beta, whereas kappa is much less hydrophobic or very less hydrophobic. So, those which are hydrophobic, they are inside, interior, not in the outer periphery. So, that the water, that is hydro part, is away from them, whereas the kappa casein, which is not so hydrophobic, is on the surface, on the periphery, so that water molecules are not so much repelled. Otherwise, what will happen? Everything will come down and the colloid will be disturbed. And if the colloid is disturbed, then it will drop down. So, that is not happening. So, how the mechanism is that alpha beta, those which are hydrophobic, they are in the interior of the micelle, whereas in the exterior of the micelle, that is in the surface or periphery part, this is the kappa casein which is there, for which the stability of the colloid is there in the milk, right. The hydrophilic protruding chain of the kappa casein protrudes from surface of the submicelle, forming a hairy layer which is around 5 to 10 nanometer in size. This hairy layer which we have seen here like that. So, these hairy layers are around 5 to 10 nanometer in size, right. You remember we said the micelle is around 0.4 micrometer, right, and these hairy submicelles are around 5 to 10 nanometers, right. Kappa casein is deficient submicelle. Kappa casein deficient submicelles are mainly located in the center of the micelle, whereas kappa casein rich submicelle predominate on the surface, giving whole micelle a hairy surface layer, right. So, those which are not so bad with water, they can stay with water. So, they will be on the periphery, on the surface, whereas those which are hydrophobic, they are in the interior of the micelle and they are hydrophobic in nature. Hairy layer of kappa casein's protruding chain is partially responsible for the micelle stability through a major contribution to the negative charge of the micelle. And calcium phosphate and hydrophobic interactions, calcium phosphate and hydrophobic interactions between submicelles are responsible for the integrity of the casein micelle, right. So, these phosphates which are present in casein, they are hydrophilic. So, they counteract the hydrophobicity, right. So, they counteract the hydrophobicity and more phosphate groups are there, better the colloidal stability. No? So, now adding an excess calcium and phosphate results in aggregation of submicelle into larger units of micelles. So, if you have more calcium, that is binding material which binds the submicelles. So, when you have those binding materials like calcium or phosphates, so they bound or they bind rather the submicelles and they form larger units. These submicelles then form larger units and more stability towards the colloidal suspension of the or colloidal nature of the protein in milk. Reason for this aggregation is presumably due to the deposition of calcium phosphate in the submicelle, which lowers their electric charge and make them more compact, right. Then this is how the casein phosphoprotein, these are helping in stabilizing the micelle. You see, the earlier I said in earlier class that the this amino acids, these amino acids are in the sequences, right. Here also you see in beta casein, we have you see this GLU, that is gluten or gluten, and then SCR, then LU, then SCR, then SCR, then SCR, then GLU, that is different. And I did not show you that one. I have seen that how in the next class, okay, I will show you that how that glycine, GLU could be glycine. So, this glycine or no glutamic acid, this could be glutamic acid or glutamate, right. So, glycine, glutamate, how they are abbreviated or how they are getting that that coding, this I will tell you in the subsequent class. Okay. However, we see here that this is like that. So, in the 15th position, this is the one phosphate, in 17th position another phosphate, in 18th position another phosphate, in 19th position another phosphate, like that in 35th position another phosphate. So, these are normally in the beta glycine or beta casein. Then in alpha S1 casein it is more, it is 46 position one phosphate, 8 position one phosphate, 64th position another phosphate, and then 66 position another phosphate, then 67, 68, like that, even 114 position some phosphates are there. This is the how casein and phosphates they are linked. Then alpha S2 casein, in that it is S2, we if you remember in earlier class we had said that alpha S1 is more hydrophobic than alpha S2, right. Alpha S2 is much less. Here you see the reason is that here it is from 8th position, 9th position, 10th position, where it was 15, 46 these positions, right. So, up to 61, 56, so many. So, because of that this alpha S2 are having your lot of hydrophilic nature than that of the alpha S1, right. So, because of the presence of the phosphate groups, right. Similarly, kappa casein, this of course is having very less phosphate, because kappa casein otherwise because of the chain or because of the composition of the this your this carbon chain, not only carbon chain, that because of the composition of the your acid, this what we call, or just now we said that because of this composition of the amino acids. So, this amino acids, because of that the how they are linked, by which of the amino acids the kappa casein is having more hydrophobicity, less hydrophobicity or more hydrophilic nature, right. So, this is how they are coming. Now, let let us look into that Casein precipitation. Casein precipitation happens. One characteristic property of casein is its ability to precipitate at pH 4.6. That is, isoelectric point of the casein is 4.6, right. You remember that we had said that these caseins, they do have charge, right, and when you are adding this acid, that means you are adding some more charges. So, they are neutralizing. So, when it becomes that isoelectric point 4.6, then that corresponds to the sedimentation of the separation of the casein. That is how casein precipitates, right. Due to the complex nature of the casein molecules and that of the micelle formed from them, precipitation can be caused by a number of factors or agents, right. Number of factors or agents. So, that is responsible for the precipitation of the casein, right. So, now let us look into the other part of the casein, that it is a snow white, odorless, tasteless, granular substance, contributes to the whiteness of the milk. This is one property of casein, found in combination with calcium as calcium caseinate, dispersed state as colloidal suspension. On boiling freshly milk, thin layer of finely precipitated casein together with other milk constituents including fat forms a thin layer over the surface of the milk with added acid it curdles. This we said also earlier, that when mummy and others we have seen, when they are boiling milk, that what is happening, this casein or the protein, both soluble and insoluble, because at high temperature you are boiling. So, the whey protein also becomes insoluble. So, both whey protein and casein, they come out, not only these two, but also along with that fat and many others, they do come out, form a fine layer or crust on the surface of the milk, which does not allow the vaporization of the water from inside, thereby is giving our upward thrust, for which the crust becomes swollen and then ultimately it spills over, right. So, this is how the spilling of the milk during boiling is occurring, right. And if there is high acidity, then it curdles, that is also already discussed, right. Now, where it is used? Casein is used mainly in manufacturing of hard, water resistant, non-inflammable plastics, right. High quality plastics like celluloids, those where photographs are being taken, they are made of casein, because casein and a great quantity of casein is used there. High quality of comb, there also casein is used. High quality of this glass frames, there casein is used, right. So, casein is really having very wide utilization or usability, right. This is substitute for this celluloid, horn, tortoise shell, a wide variety of toilet articles such as comb, button or rims for eyeglasses. Fountain pen barrels, electrical insulations, high grade paper, around 80% of casein is used. We see paper qualities of different type, right. Not only the paper on which you are writing normally, not only on the leaflets which are of very poor quality, but also we get very great quality of papers where good photographs and other things are impregnated or printed, right. So, those high grade, high quality papers, they are also made of protein, this casein, and to the tune of 80% of the casein is used for that, right. So, for very great quality of paper manufacturing, you need very good quality of protein or good quantity also of protein. Then in forming glue or cold water paint, this protein is also used or casein is also used, right. Then we come to the other use, that is, it is also used in textile, it is also used in textile and leather industries as spreader over foliage, that is horticultural work, or to spread and adhere better as casein fiber or aralac is there, or it forms as in hat industry, in the manufacture of fur felt hats, right. In typically those where cold systems are there, right, cold weather is there, there you have seen people are using lot many fur hats, right. Those fur hats, they are also being produced from the casein. This casein has a wide, variety, wide application, and fortunately the casein availability is also there, that is why the price could be controlled. But mind it, all this protein is coming from milk. So, at the cost of defatted and then you are deproteinated milk you are using, because this casein you are getting separated, right. This casein you are getting separated from the milk. So, you are left with whey, right. So, unless casein you are precipitating, they are not, you are not also getting the casein. So, that means that milk which is say 100 milliliter or 100 gram, out of which 4 gram only protein you are getting, right. So, you are 100 milliliter, 100 milliliter of milk you are wasting for 4 gram of the casein because of this kind of use. So, as a dairy person or as a part of the dairy, you will obviously not want, unless and until you have enough quantity of milk produced, you will not be allowing this to happen, that use of casein for some or other purpose. Because again, as we have seen that in the milk fat, it is more assimilable than many other fats. Similarly, this milk protein is better assimilable in the body system than many others, right. So, everything we cannot just tell on the blackboard or on the board itself, because that does not encompass in our course curricula, otherwise we will not be able to finish up, right. So, the last use is that filler or binder in certain foods and serves as the base material for a meat sauce and as a binder in sausages. So, we have seen at home also that in many cases that binders are being used for binding. For a small example, that many times you might have seen that mummy and others, they are making dishes. maybe from the peel of some of the vegetables. These peels you cannot fry, they become individual, you cannot make them complex or compact. So, to make them compact, you have to have some binder. So, this binder, this casein can be acted as the binder or filler agent, that is filler unit. So, that binding or filling, this can be done with the help of this casein, and this helps in making different dishes like sauces or sausages. Many such kind of things are being done with the help of the casein, right. So, with this, let us stop casein today. As I promised that in the next class, I will show you how the naming alphabet A, B, C, D, E, F, how this naming for the amino acids are being done, right. Thank you.